screen?
Yep. There you go. Can you see it?
Yes. Can you go
Now it
full
should be going full
screen?
screen. Should be now.
Yeah, great.
Looks good. Great.
Yep.
Can you hear me
Yeah.
fine?
Sorry?
Can you hear me fine?
Yeah.
Good, good.
All right. So our second speaker today is Michelangelo Tartaglia from IFT Madrid, and he will be talking about quadratically refined discrete anomaly cancellation. Michelangelo, please go ahead.
All right. Thanks a lot. So first of all, thank you all for coming, and let me thank the organizer for the invitation, of course. Today I'm going to talk to you about this work with Marcos Dirigal in CERN about anomaly cancellation, and in particular in the setup of discrete symmetries in six-dimensional theories. So I'm going to start the talk with an overview of global anomalies in six-dimensional theory, what are the anomalous degrees of freedom, and why these anomalies are subtle and a bit complicated, but also very interesting. Then I'm going to discuss our setup in a bit more detail and give sort of the logical structure of the argument that allows us to get constraints on fermions with charge zk that allow for this mechanism of anomaly cancellation that I'm going to describe. Then I'm going to spend some time with some more details, in particular about the anomalies of self-dual two-form, since I assume most people are not, or at least less familiar with those rather than fermions, and then some more details about how the calculation concretely goes. Lastly, I'm going to mention another constraint, which is in some sense independent from the rest of the anomaly cancellation constraints, and depends more on consistency about changes of spring structure. And lastly, I'm going to summarize and conclude. So let me start with an overview on anomalies very quickly. Like the story is the usual one. Suppose you have some symmetry of your classical theory represented by a group G, which leaves the classical action invariant. Then it's very well known this might not survive quantization. And one way to see this is that thinking that in the quantum theory, the fundamental object is not really the action, but rather the quantum partition function, which has some more information. And traditional ways to see this anomaly is, for example, through the non-invariance of the measure in the path integral. This is the famous Fujikawa method. Or to the failure of some word identities. There are some correlators which contain divergences of currents. They should be zero classically, but turn out they're not quantum mechanically. And they give some polynomials like this famous ABJ anomaly, trace f squared, which contain the same information as the change of the phase of the partition function among these anomalous transformations. So in particular, for gauge transformation, we really don't want to have anomalies. Like I remind you that gauge transformation allow us to get rid of negative norm states. So it's something that we really want to preserve in the quantum theory. And sometimes there are theories which naively look anomalous, like they have some term like the one I showed before, but can still be saved with a mechanism called the Green-Schwarz mechanism. Concretely, let's do it directly in 6 dimension and assume that there's a transformation which acts on our gauge fields, transformed A into some transformed A lambda, and the partition function changes by a phase, which is precisely the anomaly. And if you assume that the anomaly factorizes like this as a product of a 2-form and a 4-form, and furthermore, in the theory, there's also a coupling of a dynamical 2-form B to the same 4-form X, then one can make the full theory non-anomalous, even if naively it seems so, by imposing that under the same transformation lambda, B2 also transforms in this way below, that, as you can see, clearly gives the opposite phase. So overall, it cancels. In our work, we're going to implement something similar, but with a couple key differences. One is that we don't have to impose this extra transformation, let's say, because we were going to work with self-dual 2-forms B, which are anomalous on their own. And we're going to leverage this anomaly that they already possess to balance out the anomaly that the rest of the degrees of freedom, namely the fermions in our theory, are going to have. And the second difference is that this language doesn't quite apply because we're going to focus on discrete symmetries, particularly ZK. There's a couple ways to see that this doesn't work. One is that all the field strengths are zero. So the polynomials of the one that I showed before are always going to be zero. And the other, there's no small gauge transformation, nothing which is generated infinitesimally. If you think about ZK, you can only do discrete jumps transformation. Anomalies associated to these kind of transformations are usually called global anomalies. The naming is a bit weird. Like we're always going to be talking about gauge symmetries. There's no global symmetries in our talk. The global here is used mostly as opposed to local or perturbative anomalies, but that's the name people usually use, so I'm going to use it global. And this kind of anomaly necessitate a more involved mathematical treatment, mostly because what I said, the field strengths vanish, so we can not really use differential force, but I'm gonna talk about this more later. The other ingredient we have, as I mentioned, there are in 6 dimensions, there are self-dual 2 forms, which are anomalous on their own. And the proper quantization and description of your theory is notoriously complicated and subtle and depends on some topological data. Among this, there's something which is called a quadratic refinement. We're not going to talk at length about at length in this talk. What we do in our work is put together these ingredients and sort of systematically find the constraints on the fermionic spectra which allowed a mechanism like this to happen. So, as I said, let me discuss a bit what I mean by global anomalies. There's a modern perspective which is needed, and this is that the anomaly of a d-dimensional theory is encoded in a topological quantum field theory in one dimension up, which is called the anomaly theory. And how it works is roughly as follows. One sort of geometrizes the problem. So we take 2 copies of our spacetime manifold, where we define our theory, and on one hand put some gauge configuration labeled by A, and then on the other hand, they transform about the transformation lambda as I described before, and sort of sweep it through this interval. And what we want to measure is the difference in the partition function on either side of this interval. What we can do, since the 2 gauge fields are gauge transforms of one another, they're equivalent, they describe sort of the same geometrical object, is gluing the 2 sides of this interval to give what's called a map in torus. And it turns out that the difference in phase of the partition function is given precisely by evaluating this anomaly theory that I mentioned on this torus. Let me take this chance to stress that anomalies in my convention appear always in the exponents and with a 2 pi I in front. So every single equation I'm going to write down in this talk is valid up to integers, because as you can see from this expression, having an anomaly that's just 0 on the nose or evaluate only 2 integers is exactly the same. For concreteness, for chiral fermions, this has been known for a very long time. The anomaly theory is given by this topological quantity called eta invariant, whose full definition doesn't really matter for us today. I'm just going to leverage a couple of properties of it. The first one is that when the transformation lambda that sort of sweeps through this torus is perturbative, so continuously connected to the identity, this eta invariant evaluates precisely to an integral over some polynomial in the field strengths, which is exactly what I wrote down before in a simple case, but what the perturbative framework gives. When this is not the case, when the anomaly is not perturbative, this is always going to be the case for us. One, in principle, should compute directly the eta invariance. This is usually very hard to do, but there's another important properties that they enjoy, which is that they're Bordism invariant. What does this mean? You have some configuration like this with 2 manifolds y1 and y2, which are together form the boundary of a manifold in 1 dimension up. And if we evaluate the difference between the eta invariant on either side, is given by the integral of the same polynomial as before. So in cases where this vanishes, so where perturbative anomalies vanishes, or in our case where essentially all the field strengths vanish on their own, then there's no difference between the eta invariant on either side. This equivalence, it's a well-known equivalence relation between manifolds in mathematics, which is called Bordism. It's essentially the quotient of the set of manifolds with some properties. For us, it's going to be, well, having a zk action acting on the fields, and then some spin structure because we want fermions, quotiented out by identifying 2 manifolds if they can appear in a configuration like the one I drew. They're groups, and in particular, they're finitely generated usually. So they have, what this means is you don't have to compute eta invariance a priori. You can compute it on the generators and then use the group structure to express it on a general manifold as some linear combination of the ones of the generator. We're going to use this a lot because it's easier to compute it on generators. So let me talk a bit more about our setup. We work in a super generic setting in 6D. We don't assume supersymmetry nor any other extra symmetry apart from a gauge symmetry zk. And there's 2 kinds of field. We are anomalous under this, can be anomalous under this zk charge. They are chiral fermions. As I said before, their anomaly is given by some eta invariant, a slightly modified one. The second term you can think of as getting rid of the gravitational anomaly and really just focusing on the gauge one. So the total fermion anomaly is just given as a sum over this charges q over nq, which is just the number of fermions in your theory with that specific charge, times this eta invariant that I was talking about before. The second degree of freedom is perhaps less familiar, and it's self-dual 2 forms. And a basic consequence of the self-duality properties, which is that the star Hodge star of the field strength itself, up to perhaps a sign, is that the kinetic term vanishes. It's just by anti-symmetry of the wedge product. It's just 0. This in particular means that there is not really a simple Lagrangian description for this theory. I should mention that in the literature, there are some Lagrangian descriptions. They're a bit involved. They involve auxiliary fields, but they usually don't capture the topological global properties that we're going to need to talk about anomalies. So what we do is follow this work by Sita, Chikawa, and Yonekura, where chiral fields, so self-dual fields, are realized as boundary modes of a 7D theory, so in one dimension up, which is relatively simple. There's now a three-form A, where it's just a kinetic term, some Chern-Simons term with itself, and then a magnetic coupling to a background C, which is field rank FC. And it turns out that this theory has solutions like the one I depicted here on the right, where there's a mode B with the equations of motion fixed to be self-dual, and with sort of damping term that localize it somehow near the boundary. Taking the m to infinity limit of this kind of theory achieves two things at the same time. One, you can sort of see from the picture, it sort of squeezes this mode really to be on the boundary. So in some sense, we have an honest self-dual field on the 6D boundary. And the other is that turns out that the m to infinity limit of this action here, put in a partition function, is exactly the anomaly theory of the self-dual field. Let me stress an important detail here, which is this Chern-Simons term is at level 1/2, half integers. And this, as I'm going to argue in a second, is going to bring the need arises to use a quadratic refinement, this object I mentioned in the beginning. Concretely, the anomaly in this language you get from the equations of motion is just a Chern-Simons term again, now with the background C, at level 1/2, up to a sign kappa, which depends on self or anti-self duality. Importantly, that there is division by 2, which seems very harmless, written like this, but it turns out it's very subtle to define it properly. And the actual way to do it, to be well defined, is to use a quadratic refinement. So I'm going to denote from now on the tensor anomaly like this. Since I assume most of you have never heard of this, or probably very little, I'm going to give you overall properties of the quadratic refinement very quickly. So the definition is a bit abstract, given to a billion groups, so things you can multiply by integers with some multiplication. Quadratic refinement is a function that satisfies this property. It looks very abstract, but concretely with example, it's easy to see what this is doing. For example, take the real numbers with the usual multiplication. A function that satisfies these properties upstairs is just x squared over 2. So what is this telling us? That a quadratic refinement really is a quadratic function in the most straightforward meaning of the term. It's just x squared. But importantly, it's dividing by 2, which is what we want to implement in our Chern-Simons term. Slightly more interesting, but very enlightening, is the case of the integers. Here it's basically the same, but there's an obvious problem, which is that if you divide an odd number by 2, you don't get an integer again. There's an easy fix for that to get a function which is well defined, which is adding a linear term instead of x squared, just x times x plus 1. This, as simple as it is, illustrates perfectly what quadratic refinements do in more complicated spaces of what we're going to use. It's the proper way to divide sort of a product by 2 in spaces where division by 2 may not naively be well defined. And let me note another thing which is going to be very important in our actual case in the following, which is I wrote x times x plus 1, but I just as well could have written x times x plus 3 or plus 5 or any odd number. This still ensures that the numerator is even. So in particular, for any given group and pairing, there's many, possibly infinite quadratic refinements. There's ambiguity, and one has to make some choice. So given this, I'm going to just very quick calculation, a property of these quadratic refinements. If you take multiples of a single element, you can just write them as x plus x plus x plus x. And this gives you a simple recursion relation, which gives the value of n times some element in terms of the value of the element itself. And this is a property that every quadratic refinement like this has to satisfy. And this is very general, and we're going to use it to constrain fermionic spectra, as in the following. So here this is the summary of our work very quickly. We just impose that the total anomaly cancels, that the fermionic anomaly plus the tensor anomaly adds up to 0. This can be easily rewritten like this. And this simple equation gives actually a lot of consequences. First of all, the left-hand side is a Bordism invariant, as I argued in the beginning, it's some sum of eta invariants. So the right-hand side should be as well for this to make sense on any manifold. And this means two things, in particular that we need to find a quadratic refinement which is a Bordism invariant. This is not obvious at all if you just write down a function. But then once we found it, we can again are allowed of just computing it on generators and then using the Bordism relation to find the value on a generic manifold and ensure that it cancels everywhere. Conversely, the right-hand side is a quadratic refinement. It's a quadratic function in the sense I said before. So the left-hand side should be as well. But there's no reason for this to be the case for a generic spectrum. If you just write a linear combination of eta invariants, there's really no sense in which it's quadratic in the background. So this is something we have to impose. And in particular, with the recursion relation I wrote in the previous slide, we can get pretty strong constraints on the fermionic spectrum. So let me now show you a slide with our results, the main results of our paper. We go case by case in ZK, and here's the Bordesian group that we are interested in, with the generators that are well known. I'll show it later. Some were known in the literature already, some we actually computed. And then the first column on the left is constraints, which are given just by imposing that the fermionic anomaly, since it's equal to the tensor anomaly, is quadratic in the background, in a very generic sense, without picking a specific quadratic refinement. And they give you this constraint, which are already pretty stringent. On the right, like the rightmost column, then we specify quadratic refinement given by this parameter R, which I'm gonna describe a bit more later, and refine this condition to a specific subgroup on the one on the left. Okay. Now, as I promised, some more details about how this calculation goes. First, recall that we said that we want to represent self-dual field as boundary modes of this theory here. But I also said at the very beginning that we're dealing with discrete fields, with morally like all the field strength vanish. What this means is that this language of differential forms is really not appropriate to describe these topological effects. We need something a bit more general. The solution to this is a framework called differential cohomology. I will not give the full definitions because it's really not important. The point is that you can represent a gauge field as a triplet, where N, A, and F, where A and F are what you're used to. It's just the gauge field and its field strength. But there's this extra piece of information, N, which contains information about holonomies of A, so global effects. And essentially, it parameterizes the failure to be a globally defined differential form. Like on general manifold, gauge fields are not differentiable everywhere, only locally. The other thing you need to know about this is that there's a pairing defined up to integers on this space. And then when n is equal to 0, so when this extra piece of information you can forget about because it's not there, fields are called topologically trivial, and the pairing is just a Chern-Simons term. So this makes it clear that this is the good generalization for what we wanted to do, which is writing a Chern-Simons term and divided by 2. Then, using this language, the honest way to write the 7D bulk theory I was writing is like this. We are just replacing the magnetic coupling between A and C with the pairing, and the Chern-Simons at level 1/2 with the quadratic refinement. But as I was saying before with the integers, already in that very easy case, there's ambiguity. You can choose different quadratic refinements. You can imagine that in a complicated space like this, there's a priori many more you can choose. So fair question is which one we should use. This is not obvious a priori. What we do is we follow and generalize a procedure from this paper when they give a quadratic refinement, which is explicitly Bordesian invariant. I won't prove it here, but it is, which looks something like this. If you stare at it, it looks pretty similar to the simple case of the integers. There's a quadratic term in the field strength FC, and then a linear term shifted by this class, P1, which appears because it has this very interesting property, which is it's called the VU class, which is defined as these properties down below, which means that this product with any 4 form X4 is even, integrates to an even number. What does this mean? That it's defined up to even numbers, it's fine to divide it by 2. It's not a problem. So this is really the way to implement division by 2 in this bit more complicated context, but it sort of looks like the integers. And it has a similar ambiguities. So we generalized a bit. There's 2 things we can add. One is a non-minimal coupling between the dynamical field A and the background C. In the action directly like this, and this trickles down into the quadratic refinement to give it like this. And then it's exactly the same ambiguity that I was talking about with the integers. I could have written 3, 5, or any odd numbers. I can do the same here. Any odd multiple of this VU class is allowed and gives a well-defined quadratic refinement. So this is what we're going to use. Now, the thing is, can we actually compute this? On a general manifold, it's hard. I don't know how to do it, but again, we can use Bordesian invariants. The Bordesian groups here are the ones we're using, and the generators are known, and they're given by length spaces. A length space is some quotients of a sphere by an appropriate ZK action, which naturally comes equipped with the ZK bundle, so the object we want to study, induced by the quotient. Simply, the fiber is going to be a ZK. Other bundles, it turns out, on these spaces are just multiples of the defining one. You can take the connection on this one that I was writing above and multiply by an integer C, which is defined only mod K on ZK bundles. And this integer C is the one we're going to run the recursion relation that I was writing a while ago about any quadratic refinement. In particular, length spaces are also nice because all the ingredients in our a priori complicated construction are known. It's known how to compute the non-length spaces. Eta invariants look like this. It's not a particularly nice looking formula, but the point is you can compute it and it gives you a number. And the differential cohomology is very complicated a priori. Here is just a simple ZK group with one generator we call X. And the pairing is also simple. Given multiples n and m of this generator, it's just this fraction, minus mn over k. Plugging all this in the general framework gives a recursion relation on the fermionic anomaly. So the fermionic anomaly in the background C, labeled by this integer C that I was mentioning before, is just given in terms of the one on the defining bundle with the expression on the right-hand side of this equation. And this is the one that we imposed to derive the first column of this table. This is essentially what we did. What I'm missing in this table, which I haven't described to you, now it's the rightmost column, this parameter R. This is given on the quadratic, on the tensor anomaly side. But again, since the pairing is so simple, you remember it's just minus m times n over k for multiples of the generators. It's not hard to play around a bit with the algebra and the defining properties of this quadratic refinement and see that there's only finitely many of them. They all look like this, parameterized by an ambiguity given by an integer r, which matters only mod k, like this. Then our quadratic refinements, the explicit expression we wrote down before, in terms of the coupling J and this ambiguity in the definition of the quadratic refinement L, looks like this. And there's not a really nice closed formula, but once you fix K, it's very easy to match these two expressions and write off R as a function of J and L, and then plug it back into this table here and get the finest constraint. Okay, finally, I want to talk about the extra constraint that I mentioned at the beginning, which comes from spin structures. It's not directly follows from what I said before, but it's still interesting. And the key observation is that both the eta invariants, since they depend on fermion, this is perhaps not surprising, but also our quadratic refinements depend on the choice of spin structure. This was first highlighted in this math paper by Hopkins and Singer. What we did is compute this dependence explicitly on our Born generator on the length basis. This is possible. It gives something like this. The first two tables are the variation in the fermion anomaly on these generators, while the bottom two are the variation in the tensor anomaly. But since they're the same, right, they're related by an equal sign. If they were the same before the change of spin structure, they better be the same afterwards as well. So by matching these changes in the two table, we get some extra constraint depending on the parity of k, rather its value mod 4. And this is in a sense independent from the other anomaly cancellation condition, which is quite interesting. In particular, if it's not satisfied, if one could find perhaps from top-down a theory which satisfies the other constraints, but not this one, it would perhaps hint at some other form of the quadratic refinement, which is not covered by our parameterization and the sort of straightforwardly Born invariant one. Okay, so let me conclude and summarize. What we did in this work is sort of systematically investigate the constraints that a mechanism similar to the Green-Schwarz, just adapted to this case, imposes on spectra in 6 dimensions, very generally. I have to mention that there's an upcoming work which verifies from top down our constraints in F-theory models, and they are verified in models where the fermion anomaly does not vanish on its own, which hints at this mechanism, this anomaly cancellation between fermions and tensor being really what's going on. Again, let me stress that we work purely bottom up with generic quadratic refinement and no extra assumption. And this really didn't constrain the quadratic refinement itself. So maybe a top-down scan of what's possible in string theory, even in supergravity, could hint about restrictions on the choice of the quadratic refinements that we used. And finally, as some questions for the future, natural one is adding more tensor field. We did the systematic analysis only with one because it's the most stringent constraint. Like if you add more tensor field, you have more degrees of freedom, you can sort of cancel more anomaly, but it could be interesting to do it systematically. And finally, doing the same for U1s would be interesting. U1 is in a sense more complicated for two reasons. One, you have also perturbative anomalies to take care of. In our setting, it's purely non-perturbative. And there's also not a finite number of quadratic refinements that you can write down. It's actually infinite. So it's a bit more trickier to do it fully systematically. And as a very last thing, let me mention that these tensor fields in supergravity theories, for example, have some duality actions acting on them. So it could be interesting to investigate if this have anything to do in something more to say in this story. All right, I'll leave it at that. Thank you.
Thank you, Michelangelo, for the very nice talk. Are there any questions? Yep. Florent, you can. Okay.
Yeah.
Please.
Hi, thanks. Very nice talk. I have two quick questions. First of all, is it Is your setup with supergravity, or does it work also for where gravity is decoupled?
Yeah. It's so super certainly not. We don't assume supersymmetry. Sort of the idea started from that, but then we realized we really didn't need it.
Right.
Where gravity would enter explicitly is that for the self-dual field in the gravity multiplet, let's say kappa is equal +1. Right. So if you do gravitational theory, you for free have one self-dual field. And then in supergravity, you have T, like any number of tensor model with anti-self-dual. But other than
Okay.
that, it's not really specific to any of this setting. You can write down a theory with just anti-self-dual ones. It's not going to be gravitational.
And you're at the end, you were mentioning excluding possible models. Is there a very simple model where it looks fine for from at the level of like the fermionic anomaly, but with your results, it would be excluded?
Exclude I wouldn't say, because like these are precisely models which, if you only look at the fermionic anomaly, don't look fine. Right? The fermionic anomaly does not vanish on its own.
Oh, okay. That
Right?
makes sense. Okay.
That's obviously a valid solution, that there's no fermionic anomaly and there's no tensor anomaly, then nothing is anomalous and it's done. But these are models where this cancellation is actually happening.
Okay, cool. Thanks a lot.
Yeah, there are a couple of questions from Max Planck Group. Can you unmute yourself, maybe? No.
Hi,
Oh, yeah,
hi,
there
Miguel.
is.
Thank you for the very nice talk. Can you hear me well?
Yeah.
Now, yes. Yeah.
Okay, I just wanted to ask, what does it mean to, when you do this shifted eta, what does it mean to take away the gravitational anomaly? Do you fix the area of genus or something like that?
Yeah, I mean, I lied a little bit, as in I said in our case this cancels, but of course the F part cancels for discrete anomaly. There's still the A roof genus, right? In the eta invariant. So if you take differences of eta invariants, the one that's with the Dirac operator coupled to the charged representation minus the one with the neutral one, then you get rid of the gravitational anomaly.
Oh, right, I see.
We did it because we only want to focus on that. Of course, if you want to do, like, if you include, the point is the gravitational anomaly, you could always cancel with uncharged degrees of freedom. So we wanted to focus on the gauge one because our constraints cannot see uncharged things.
I see.
But the
Thanks.
gravitational anomaly cancellation is separate from what we do.
Right. Thank you.
Okay, there is another question from Paul. Yeah, please, Paul.
Yeah. Hi, Michelangelo. Yeah, very nice talk. Very enjoyable. So yeah, just two quick questions. So on your outlook at the very end with the U1 cases, I mean, do you mean U1 together with ZKs, or because U1s by itself, I would expect only to have perturbative anomalies, or what do you want to get there?
Yeah, that's fair actually. Yeah, I didn't say it well. Yeah, you have perturbative anomaly, of course. The Bordism vanishes. I guess the more ambiguity is with the Bordism, right? You cannot count them and finally, like, you don't have a finite number of them. So the more complicated part is about classifying this quadratic refinement and seeing if there's
Okay,
an
it's
ambiguity.
really about the quadratic refinements. Okay, yeah, got it.
Yeah. Thank you. That's the better way to say it.
Okay, I understand. And then the other thing is, so that's a bit, so when you, for example, when you look at the Z5 anomalies, so Z5 typically has, like, two Borism generators, the group, and but you get only one condition. Is it clear why this is?
No,
Yeah.
why not? The one on the, so I think I have some backup on the Bordism group. Of course, there's the other generator on the multiple with K3s.
Yeah.
Without fixing the quadratic refinement, so the generic ones just by these recursions, the one on that generator is weaker. So it's actually implied by the other ones already.
Okay.
I
But
don't
that's
have
that.
a purely conceptual explanation for that. It
Yeah.
happens to be the case in every case.
And it's like something you would expect only for a single tensor field, might not hold for more.
Um,
For if there would be more anti-subtle tensors or so.
I would, so I wouldn't tell you for sure, but I would expect it to hold still because
Okay.
the recur. So of course you wouldn't have like a sort of one-dimensional space. You will have a bigger one,
Mm.
but this recursion
Mhm.
relation, which is as far as I can see, the one we can really impose without making a choice, is sort of about taking one direction and seeing the multiples in that direction.
I
And
see.
fixing a direction, the same thing should hold. That the weaker ones, like K3 gives you an overall factor in front of every
Sure.
fermionic anomaly, and so it's less restrictive, sort of.
That's right. Okay, good. Yeah, thanks.
All right. Are there any other questions? Okay. If not, let's thank the speakers.